Hey, everybody. It's Friday, May 21st. And as you can see here in the aim today, our goal for today's video is all about how we can describe the features of a periodic wave. Now, yesterday we introduced ideas about waves. In yesterday's video, we made attempts to ask and answer basic questions like what is a wave? What are the different types of waves? How are waves generated? What is the difference between a wave and a pulse? Or what is the difference between a periodic wave and a pulse? And what's the difference between a transverse and a longitudinal wave? Now, all of that information is important and relevant to the course. But if we want to summarize what we said yesterday, that's really critically important to today's discussion, it would be as follows. A wave is energy. Waves are caused by vibrations or oscillations. Oscillations are motions back and forth between two extremes. So when an object is vibrating, it causes energy to be sent out in space. That energy takes the form of a wave. What is unique about waves, what makes them fundamentally different than particles, is that waves transmit energy without transmitting mass. It is energy traveling from one point to another point in the form of this thing we call a wave. Now, I think this part of the discussion is really important because I certainly remember when I was first learning physics, I would often find myself coming back to the question like, okay, yeah, I see all this stuff, but like, what is a wave actually? And I think it's important to realize a wave is just energy. Now, oftentimes when we ask what is a wave, we're shown a picture that looks like this. And they say, like, well, this is a wave. And I think there's a lot that we can say about this picture that I want to talk about this picture right now, because I think in a lot of ways, this picture can give you like misleading conceptions of what a wave actually is. A wave is just energy. So if we ask the question, what does a wave look like? Showing this picture as the answer to that question is not so great. And the reason why I don't like to just show this picture when people ask, well, what is a wave? What does it look like? Is because it's important to remember a wave is just energy. You can't see energy. We don't even really know what energy exactly is, if you remember back to the energy unit. And so we have to be really, really careful about the way we describe this picture. The first thing we should say is this picture should look somewhat familiar to you, right? It looks like a sine curve. And what a sine curve is, it is a graph, really, of position versus time of an object that is moving back and forth. That's the basic detail. When an object vibrates back and forth, if it goes up and down and up and down and up and down in a sort of smooth fashion, if we graphed its height as a function of time, it would end up looking something like this. We can actually make this point pretty simply here with a basic video that shows this exactly. And so notice here in this particular video, you're going to see something that's moving back and forth. And when that thing moves back and forth, if we literally just trace out its position, it looks like a sine curve. Notice the actual object is just moving back and forth in a straight line. But if we were to plot that as a function of time, which is represented here by the scrolling of this piece of paper, then we see that classic sine curve. Now, that can sort of, to some degree, help us to answer the question, what is a wave? Because a wave is not a drawing. This is just a representation of what is happening to the particles in the medium. And I think that's a really important point for us to stick on for a second. Remember, yesterday, we said a medium is the material the wave is actually traveling through. Remember, the wave is just energy, so the medium is the material the energy is traveling to. Let's just take the example of a slinky. If we are shaking the end of a slinky and seeing how the waves move through the slinky, then the medium for this wave would be the slinky. And essentially what this picture is showing is what the slinky would look like. Notice I didn't say the wave, I said the slinky, which is the medium. This picture is showing what the medium looks like when the wave travels through the medium. Remember, a wave is just energy. I think this simulator really helps to sort of put a pin on the point here. So notice I can adjust the features in this simulator to sort of make this thing look more like a traditional wave. And so if you notice, what we see here in this simulator is that we see this wave. It's moving from left to right. What these purple dots are showing you is what the particles in the medium are doing. So notice the reason why this green line is squiggly like this is because basically what we're saying is the wave is energy, which tells the particles in the medium what to do. The particles in the medium, in response to this energy moving through the medium, are going to just move up and down and up and down and up and down. And that's the idea. When the energy travels through the medium, it influences the particles in the medium. And if we actually trace out what these particles are doing over time, moving up and down and up and down and up and down, we see this sine curve-like looking shape, which is why we often represent a wave as a sine curve looking particle or as a sine curve looking graph that ends up looking something like this. And so the basic idea is this is just a graph. If something is moving up and down and up and down and up and down, if you look at its actual motion, it just looks like this. But if you plot it as a function of time, it ends up looking like that. And so we need to be very clear about what we're saying here. And so I want you to write down this note. After one full cycle, it's going to be really important that we define these things in terms of cycles, because notice this thing is experiencing regular, repeated, or to put a fancy term on it, periodic motion, just a regularly repeating pattern. After one full cycle, a particle in the medium, starting at its equilibrium position, will have gone up to its maximum positive displacement, down through the equilibrium position and to its maximum negative displacement, and then back up to the equilibrium position where it started. It goes up, down, and back again. So notice here what we're basically saying is the equilibrium position is the starting point, and I'll write this here. Abbreviating equilibrium is EQ, the equilibrium position. This thing is going to go up, down, and back again. You should really write that down because that is a picture of one full cycle. The object starts at its equilibrium position. It goes up to its max positive displacement. It goes back down to the equilibrium position. It comes down to its max negative displacement and then back to the equilibrium position. So notice in one full cycle, it's sort of either touched or crossed the x-axis 3 times. It goes up, down, and back again. That's the definition of one full cycle. And as you'll see here in a little bit, that's very important because a periodic wave is really just a series of regularly repeating patterns that tell the particles in the medium to just move up, down, up, down, up, down, over and over and over. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so very quickly before we move on here, I think I want to focus in on this picture of a cycle because the concept of a cycle is very, very important when we're talking about basic characteristics of a wave. Notice here, this thing goes up, it comes down, and then it goes back again. And so we can identify a cycle by literally tracing it out and say, okay, it starts at the equilibrium position, it goes up, then it comes down, then it goes down, then it comes back. Okay, that's one full cycle. But since this particular picture of the wave is so important because the definition of a cycle is so important, we give these parts of the waves very specific names. This part of the wave here that I'm tracing in red is called the crest of the wave. It is basically like the positive bump in the picture. This crest is a basic graphical representation of the energy that tells the particles in the medium to move up. And so we either call this a crest or we call it a peak. Most of the times I will call it a peak, but the official name is a crest. The negative displacement part, and that would be this part here, is basically just a pictorial representation of the energy that tells the particles in the medium to move down. This part is referred to as the trough, which is spelled trow. It is pronounced trough. And in a lot of other cases, we call this valleys, so as to give you, the antonym of peak here. The basic idea is that pigs used to eat out of like these bucket-shaped things, and these are called troughs. And so since this kind of looks like that, they call this a trough. One full cycle, and I want to write this down because this is very important. One full cycle. Notice I have one full cycle here traced in red. One full cycle has one full peak and one full trough. That's really, really important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Moving on. This part of this video now is really the part of the video where we kick off what will eventually be a 2-day discussion about the characteristics of a periodic wave. Periodic waves have certain characteristics that are associated with their periodic nature. To be clear, what I mean by that is when a wave is formed from a regularly repeating vibration, that means like it happens the same number of times per second, then what we see is the wave that's generated by that regularly repeating vibration has some regularly occurring features that are unique to periodic waves. In other words, if I clap my hands once per second, that's a regularly repeating pattern. Or if I shake a slinky once per second, shake, 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 it will create a regularly repeating pattern in the slinky. Because of that regularly repeating pattern, there are certain things you can notice and measure about the wave. All periodic waves have 4 main defining characteristics. Those characteristics are as follows. All periodic waves have something called a period. They have a frequency. They have an amplitude, and they have a wavelength. And the reason why we spent so much of the beginning of this video talking about the definition of a cycle and the cyclic nature of periodic waves is that the definition of period, frequency, and wavelength are based on the definition of a cycle. And so it's really important for you to understand what a cycle is, because if you don't even understand what a cycle is, you will not be able to really, truly understand the definition of wavelength, frequency, and period. Again, a cycle is one full peak and one full trough. It is a full, regularly repeated pattern. It goes through all of the positive displacements and all of the negative displacements. So when a wave has completed a full cycle, the particles in the medium will have experienced all of the possible positive displacements and all of the possible negative displacements. That's a very important idea. And so the basic thing here that I just want to show you again with this simulator is we can say one full cycle has been completed when the particle experiences all of the possible positive positions and all of the possible negative positions. So let's focus in on this particle here all the way at the end. You see how this particle is at the equilibrium line, the midpoint line? I'm going to start this again in slow motion. The cycle starts now. Now it's experiencing all of the possible negative positions. Now it's going to the positive side and experiencing all possible positive positions. And once it makes it back there, now we know the wave has completed a full cycle. The wave has completed a full cycle when it causes the particles in the medium to engage in this regularly repeated pattern. In other words, to experience all of the possible positive positions, all of the possible negative positions, and get back to where it started. This list here, period, frequency, amplitude, and wavelength, talking about these things, is really going to be the focus of our next 2 days. So take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, we are going to discuss the things on this list in order. That means in today's video, we are only going to get to period and frequency. On Monday, we'll get to amplitude and wavelength. So here's the deal. You probably heard the word periodic before. If something happens periodically, it means it happens at regular intervals. If you've ever heard of the word a periodical, like if you ever, took like a library class in middle school or something, a periodical is another name for a magazine. Why do they call a magazine a periodical? Because it comes out every month. So something that has a period is something that happens regularly. The period of a wave is defined as the time taken for the particles in the medium to complete one full cycle. The period is a measurement of time. Now, if you remember in the beginning of the year, many of you were presumably getting pretty mad at me because we had equations that had time in them. And you were writing a T, but it was a capitalized T. And you were saying, what's the big deal? And I said, T is another symbol in this course. The symbol for period is T. And I think it's important to realize here at this juncture, we're going to talk about the equation in a second. The equation that we are about to talk about is based entirely on the definition that we showed here at the top of the screen. The period of a wave is the time taken to complete one cycle. So if we know it takes 5 seconds to complete one cycle, well, then the period is 5. Now we can ask ourselves a simple question. What if instead of being told that it takes 5 seconds to complete one cycle, what if they told us it takes 10 seconds to complete 2 cycles? How would we figure out what the period is or the time taken to complete one cycle? Well, if we know in 10 seconds it completes 2 cycles, then if we just take 10 and we divide it by 2, then we get 5 seconds per cycle. And that's why the equation for period looks like this. The equation for period is that the period is equal to the time divided by the number of cycles experienced in that amount of time. In this equation, lowercase t stands for time, measured in seconds. Number cycles stands for the number of cycles completed by the wave. That has no unit. It is literally just a number. I will show you how to use that here in a couple of minutes. Lastly, of course, uppercase T here is period. And notice that's also measured in seconds. It should make sense to you that the period is measured in seconds also because period, notice, is defined as the time taken to complete one cycle. And that's really it for period. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now as I said, we're only going to have time today to talk about frequency and period. And I think it makes sense to just jump right into the definition of frequency. I think you'll realize why in a moment. The definition of frequency, I hope you realize just from like everyday usage of the word frequency, is that the frequency is a measurement of the number of cycles per second. How much does that thing happen every second? The symbol for frequency is F, and it is like this, a fancy italicized F. Oftentimes when you see me writing it, I will write it like that. The equation, again, is based directly on the definition. Frequency is a measurement of the number of cycles per second. So if we are given a certain number of cycles and a certain number of seconds, all you have to do is divide them. The frequency is the number of cycles divided by the time, where, of course, t is time in seconds, number of cycles is number of cycles, and f is the frequency. Now notice, if the number of cycles has no unit, so we'll just put a 1 here because it has no unit, and time, of course, is measured in seconds, that means the unit for frequency is actually the inverse second. Now, the inverse second is a really super annoying way to say the unit of something. Like if the frequency, if there were, 5 cycles per second, if we had to say, oh, the frequency is 5 inverse seconds, that's kind of an annoying thing to say. And so we decided as a physics community to name the unit for frequency after a really famous German scientist, Heinrich Hertz, who was actually the first person to generate and send a radio wave in a lab. So the unit for frequency that we are going to use is Hertz, which I'm sure you probably heard of before. The basic idea here is that when we say the frequency is 5 Hertz, what we mean is that there are 5 cycles in each individual second. Now, it's important to point out the capitalization of this unit is very important. The H in this unit is supposed to be uppercase, and the Z in this unit is supposed to be lowercase. That's very important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I hope you noticed something about these two equations when you were writing this down. Frequency is a measure of the number of cycles per second. Period is a measurement of the number of seconds per cycle. Seconds per cycle, cycles per second. You see it? If one of these quantities, period, is seconds per cycle, and the other quantity, frequency, cycles per second, that means they're inverse quantities. You just flip it over and you have the other one. This is a big note. Since the period is a measurement of the number of seconds per cycle, and the frequency is a measurement of the number of cycles per second, they're the inverse of one another. That's a very important idea. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So if you look in your reference table, you will see this idea written in the form of an equation. Now, this is on page 5 of the reference table in the new section of the reference table that's titled Waves. Notice we have now covered every single equation in the electricity section, and so we are on to the wave section. The equation for period is period equals 1 over f. Now, it should be pretty clear to everybody, but I'll just show it anyway. Of course, we could solve this equation for frequency also by writing frequency as 1 over the period. They are inverse quantities. And so this is going to be the equation that relates them. Take a second to pause this video here and write that down. And when you hit play, take a look at a problem. All right, so for the last thing in this video here, I really just wanted to show you a problem where we could put the equations we developed today to good use. This question is in the Intro to Waves packet, new packet, I guess second to last packet of the year. It's on page 5, number 3. It says, what is the period of a water wave if 4 complete waves pass a fixed point in 10 seconds? And we have a series of options. Now, there are a couple things we should say about this. The first is, what do you think they mean by the phrase 4 complete waves? What does that mean? 4 complete waves. And what I hope you realize is 4 complete waves is their way of saying the number of cycles is 4. This wave has fully completed 4 cycles. And the amount of time it takes for it to fully complete those 4 cycles is 10 seconds. And so we're looking for the period. Notice the question here, I think pretty clearly said, what is the period? Well, as we mentioned earlier, the period is defined as the time it takes for a wave to complete a cycle. So the equation is the time divided by the number of cycles. And so to find the period here, we just have to take the time they gave us, 10 seconds, and the number of cycles, 4. Notice I'm not writing 4 cycles. It is just a number. There is no unit attached to it. It literally just is a number. So we have 10 seconds over 4. And of course, for our period, we get 2.5 seconds. Now, of course, a perfectly good question for us to ask here would be, well, what does that mean? The fact that the period is 2.5 seconds tells us every cycle takes 2.5 seconds for it to be completed. And I hope that makes sense here, because they said 4 cycles take place in 10 seconds. And so it should make pretty good sense that each of them takes 2.5 seconds to happen. The first cycle takes 2.5 seconds. The second one takes 2.5 seconds. So that's 5 total. Then the third one takes 2.5 seconds. So now we're at 7.5 seconds total. And then the last one takes 2.5 seconds. And that brings us to our full time of 10 seconds. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, and moving on to the last thing here for this video, we are going to stick with this problem, but just for fun, we're going to pretend like this problem also asked us for the frequency. If this problem also asked us for the frequency, there are a number of ways we could do it, and I want to talk about both of them. The first would involve using the information that they just told us in the problem. They told us 10 seconds passes by for this thing to complete 4 cycles. And so if we want to find the frequency, we have to remember the definition of frequency is that it is a measurement of the number of cycles per second. And so we literally just take the number of cycles and we divide it by the time. And so here, if we take the number of cycles, 4, divided by the time, 10 seconds, we end up getting 4 over 10 is 0.40. And notice here we have no unit in the top, and no unit can always be treated as a 1. And then seconds in the bottom, so that would be 1 over seconds, or an inverse second, which remember is equal to a hertz. So we have 0.40 hertz. Now, I think it is important to point out, almost always, when the question actually asks you for the period, they're going to give the frequency as the answer as another answer choice, just to try to trip you up. The frequency here is 0.40 hertz, but that's not what they asked for. They asked for the period. So the frequency is 0.4 hertz. And of course, just to show you how that last equation I showed you is used here, since we had already calculated the period, we already knew it was 2.5 seconds, we could just use the basic reference table relationship between the frequency and the period to solve for the frequency. Remember, if period is equal to 1 over f, then we can simply move these terms along the equal sign, like on the diagonal. So we basically just cross multiply here. We bring the t downstairs, we bring the f upstairs, we get frequency as 1 over period. And if you take 1 divided by 2.5 seconds, in a rather unsurprising way, we get that our frequency is equal to 0.4 hertz. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, everybody, that is it for today. And obviously, because it is Friday, that is it for the week. It's really important for you to take a few things away from this video. Number 1, a wave is just energy. Representing energy in a picture is hard. And so really what we do is we try to show a way that we can represent the motion of the particles in the medium over time. Waves are energy. They travel through media, which is the plural of medium, and they make the particles in the medium vibrate. Those vibrations, if they happen periodically, give rise to certain features of the waves, like period and frequency. The period is a measurement of the number of seconds per cycle. The frequency is a measurement of the number of cycles per second. And with that, that's it for today. Have a nice weekend, everybody.